everybody. We're getting ready to do lesson 13, SAT Math Level 2 preparation. Conic sections, part 1. 26 points will go into your notebook guide, notebook sheet, and then only 2 points on your classwork. So it's mostly taking notes on part 1. Name, date, period in my classroom. Due date here for onliners and homeschoolers. And let's go right into page 1. This goes in your notebook. Geometrically, the conic sections are formed by the intersection of a plane and the two napes of a right cone. The plane does not intersect the cone's vertex, see below. In a parabola, the plane is parallel to the lateral edge of the cone. In a hyperbola, the plane is parallel to the axes of the cone. And then in an ellipse, the plane is not parallel to either a lateral edge or the axes of the cone. Intersections that contain the cone's vertex are called degenerate conics and are not covered in the level 2 math subject test. So here's a parabola, here's a plane intersecting a parabola, and then a hyperbola. Here is a plane that intersects two cones like this, and then an ellipse is here where it intersects a cone at an angle, and then that'll give you an ellipse there. Conics are also defined in terms of points in the coordinate plane. Formulas for the distance between 2 points and the distance between a point and a line are then used to define standard equations of the conics. Each conic has a pair of standard equations depending upon whether the conic has an orientation to the x or y axes. Each conic also has a center. This section develops the equations of conic sections that have centers at the origin. Because of the limited orientation of conics for the level 2 math subject test, equations for conics with centers at other points, HK, are readily obtained by horizontal and vertical translation. So circles, let's get into circles a little bit deeper here. A circle is a set of points that are equidistant, meaning the radius from a given point to center. Since the center is at the origin, the standard equation of a circle is x squared plus y squared equals r squared, where r is the radius. Circles have neither x nor y orientation. Another form of the equation of a circle is x squared over r squared plus y squared over r squared equals 1. As you will see after reviewing the ellipse section that follows, this form of the equation of a circle is similar to the equation of an ellipse. A circle with a radius 5 is shown in the figure that follows. So here is an example of a circle with a radius of 5. Here would be your rectangular. These will be your intersects here on your axes. And then parabolas. A parabola is a set of points that are equidistant from a given point. Its focus is equidistant from the focus. In a given line is directrix. The vertex of a parabola is its center at the origin. A parabola has an x orientation if its standard equation is y squared equals 4px. In this case, the focus is at the point P0 and the directrix has the equation x equals negative p. The parabola opens right if p is greater than 0 and opens left if p is less than 0. A parabola has a y orientation if its standard equation is x squared equals 4py. In this case, the focus is at the point 0p and the directrix has the equation y equals negative p. The parabola opens up if p is greater than 0 and opens down if p is less than 0. Parabolas with centers at the origin and p equals 2 are shown in the figures below. So here's two examples here of a parabola that opens up, and then this opens to the side. Y squared equals 4px, and then x squared equals 4py. That'll be this example here. The equation of parabolas that you studied in algebra never had y squared terms because these would not be graphs of functions. This should help you remember which parabolas have vertical orientation, those with y and not y squared in them. Ellipses. An ellipse is a set of points whose distances from two given points, foci, meaning the plural of focus, and a sum to a constant. So the two given points, the foci, sum to a constant. The center of an ellipse is the origin. An ellipse has an x orientation if it is elongated horizontally. Its standard equation is x squared over a squared plus y squared over b squared equals 1, a squared being larger than b squared. In this case, the major axis is the x-axis. When your a squared is underneath your x squared, the major axis would be horizontal, or the x-axis. It has endpoints negative a, 0, and then a, 0, and its length is 2a. The minor axis is the y-axis. In this situation up here, it has endpoints 0, negative b, and then 0b, and its length is 2b. For this situation, this is your minor axis. Your y squared is over your b squared, so that would mean that it is the minor axis. The foci are at c0 and negative c0, where c squared equals a squared minus b squared. Now, if you need background, students, in conics, I have tons of packets that I can provide for you. Just email me and I'll get those out to you. An ellipse has a y orientation if it is elongated vertically. Its standard equation is x squared over b squared plus y squared over a squared. See, now our y squared is over our a squared, so now it is elongated vertically, and a squared being larger than b squared. So a squared would be larger than b squared. In this case, the major axis is the y-axis. It has endpoints 0, negative a, and then 0a, and its length is 2a. The minor axis would be the x-axis in this situation because your x squared is over a b squared. It has endpoints negative b, and then b0, and then b0, and its length would be 2b. The foci are at 0, negative c, and 0c, where c squared equals a squared minus b squared. An ellipse has an x orientation if a squared, the larger of a squared and b squared, is the denominator of x squared, and has a y orientation if a squared is in the denominator of the y squared. This provides an remembering the orientation of an ellipse. Note that an ellipse with a squared equals b squared is a circle. Ellipses with the two orientations, and a equals 5 and b equals 3 and c equals 4, are shown in these figures here. So here is the situation here, x squared over 25 plus y squared over 9. So it has a horizontal major axis here. Then here are your foci. Then over here, your 25 is in the denominator of the y squared. So now it has your major axis is your vertical axis here. Hyperbolas. So for hyperbolas, a hyperbola is a set of points whose distances from two given points, the foci, differ by a constant. A hyperbola consists of two parts that correspond to the napes of a cone. Each part has a vertex and sides that are asymptotic asymptotic, sides that are asymptotic to a pair of intersecting lines. These are the lines that would be formed by a plane intersecting the vertex of the cone and containing its axes. The segment joining the two vertices is called the transverse axis. The conjugate axis is perpendicular to the transverse axis, and it is parallel to the segment between the two asymptotes that passes through a vertex. The center of a hyperbola is where the two axes intersect, so that would be right here. This is your transverse axes. This is what they call the conjugate axes, and then this is your focus here. Focus, vertex, vertex, and then these are your asymptotes here. This is your slope of your asymptote, and that is a sketch of a hyperbola and its asymptotes. A hyperbola has an x orientation. If its standard equation is x squared over a squared, again where you have our x squared over our a squared, and then our y squared minus y squared over b squared equals 1. In this case, the hyperbola opens left and right because we have a horizontal orientation. The vertices are negative a0, then a0, so negative a0 and a0. And the transverse axis has length 2a. The endpoints of the conjugate axes are 0, negative b, and 0 and b, so we're over here. This makes up our conjugate axes, and its length will be 2b. The foci are at negative c0 and then c0, where c squared equals a squared plus b squared. Now it's different than it was for the previous conic. The equations of the asymptotes are y equals plus or minus b over ax. Again, here is a sketch of that, negative b over ax. Negative b over a, this is b squared, and then this is b squared, and this is a squared here, and that's negative 3 over 4, and then 3 over 4 for the slope of our asymptotes. A hyperbola has a y orientation if its standard equation is y squared over a squared minus x squared over b squared equals 1. So now we have a y orientation because our a squared is underneath our y squared. In this case, the hyperbola opens up and down. The vertices are 0, negative a, and 0a, and the transverse axis has a length of 2a. The endpoints of the conjugate axes, in this case up here, are negative b0 and then b0, and its length is 2b. The foci are at 0, negative c, and then 0c, where c squared equals a squared plus b squared. The equations of the asymptotes are y equals plus or minus a over bx. Rather than memorize the formulas for the slopes of the asymptotes of a hyperbola, you can solve its standard equation after replacing 1 with 0. If the x squared term is positive, so y squared would equal b squared x squared over a squared, and y would equal plus or minus b over ax. If the y squared term is positive, so in this case y squared over a squared minus x squared over b squared equals 0, so y squared will equal a squared plus x squared over b squared. This is just another way of looking at these relationships so far as a hyperbola is concerned. It's kind of like an extension of the standard lessons about hyperbola. And then y equals plus or minus a over x. Two hyperbolas centered at the origin with a equals 4, b equals 3, and c equals 5 are shown in these figures here. So again, here is we have a horizontal orientation here, and then here we have a vertical orientation because our 16 is underneath our y squared, and over here our 16 is underneath our x squared, and then we have all of our other, we have a focus, and then we have our conjugate axes here. Here's our vertex, and then again here's the slopes of our asymptotes. Conics can be translated as described in chapter 12. Translations in the amounts of h and k in the horizontal and vertical directions are achieved by replacing x with x minus h, and by replacing y with y minus k in the equation of a conic. For example, the ellipse x squared over 9 plus y squared over 16 equals 1 can be translated so that its center is 2, negative 3 instead of 0, 0, by writing the equation x minus 2 squared over 9 plus y plus 3 over 16 squared, y plus 3 squared over 16 equals 1. Each point on the ellipse defined by this equation is 2 units to the right and 3 units down from the corresponding point on x squared over 9 plus y squared over 16 equals 1. So this is how you get a shift here. So for example A here, what is the length of the major axes in the ellipse x squared over 9 plus y squared over 4 equals 1? Here is a diagram of that. Major axes, minor axes. In this problem, a squared equals 9 is the larger of a squared and b squared, and a equals 3. The length of the major axes is 2a equals 6. And that was your chapter 13 conics lesson, part 1. For SAT math level 2 preparation, animated PowerPoint math video at AOL.com. For course materials and questions. Thank you very much.